fact, delivered 6 lectures already in this series.
Kindly start.
And this is the 7th lecture of Dr. Datta. And the most unique part of his lectures are he uses like a classroom the students. So go ahead, Rohini. Yeah.
Okay, sir. Yes. Thank you, sir. So good afternoon, everyone, and welcome to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly organized by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University, SPPU. So yes, today is the lecture 21 of this series, and we are nearing to the end of this series. But today we will again have our last speaker, Dr. Somenath Dutta sir from IMD Kolkata, and he will be delivering the lecture on available potential energy. And we are very glad and happy that he's again with us here. But before he delivers the lecture, I would request Dr. Mandira Shrestha, who is also Joint Secretary of SAMA from Nepal and former Water Resources Specialist, IC Mode, Kathmandu, Nepal, to please deliver the welcome address.
Very good afternoon. Thank you, Dr. Rohini. I'm extremely delighted and pleased to be providing this welcome remarks. This is actually the first time I'm attending this particular series, so I'm even eager to be part of it and also to welcome you to this 21st lecture series on available potential energy in the atmosphere, proportionality of internal and potential energy in a hydrostatic and stably stratified atmosphere. It's quite a mouthful in terms of the title itself. Now, as you just heard from Dr. Rohini, this particular lecture series, this 21st lecture series, is part of this longer lecture series that was initiated on atmospheric dynamics and its applications to climate sciences. And this was started in January early this year, and now we've come to the 21st in the series and would be ending in August. Now, as you all are aware, SAMA provides a lot of emphasis on capacity building of its member countries, and we are extremely delighted. And these lecture series are part of our flagship program that SAMA hosts, and we are delighted that we are hosting this jointly with Savitribai Phule Pune University. And this is a continued effort, like I just mentioned, of SAMA, and we put high emphasis in terms of the efforts that we make in building the capacity of our member countries. And we are also delighted to have a good amount of demand, as we can see from the number of participants that you have registered. I was just informed that there are more than 1,050 participants that have registered for this course from more than 51 countries. And that itself tells us about the need as well as the demand that we see for such kind of lectures that SAMA is eager to also provide and facilitate. Now, we are honored this time to have here with us Dr. Somenath Dutta, and I understand that he was also there in the previous lecture that you have heard from. And as you all are aware, he is a very senior scientist at the Regional Meteorological Center in the eastern region, that is in Kolkata. And I'm really delighted as well as honored that I'm here also, not only welcoming you all the participants, but also Dr. Somenath Dutta to deliver his lecture. And I'd be also learning. I'm also part of be a learner for this particular lecture series. So I'm extremely delighted. And then again, once again, would like to thank all of you and also welcome you all to this particular lecture series and taking time to attend it. So over to you, Dr. Rohini.
Thank you, ma'am. Now I request Dr. Datta sir to please.
Okay.
take the floor. Yeah.
First of all, thank you very much for giving me an opportunity to share my little knowledge with this community. So now I am sharing my screen. I hope that big board is available, is seen to everyone.
Yes, sir, we can.
So, so today I am supposed to discuss about the proportionality between the internal energy and potential energy. As we have discussed in our last class, that internal energy is given by mathematically for the entire atmosphere. It is given by this integral, that is your rho, that is density, into specific heat at constant volume CV, into temperature in absolute, and elementary volume D sigma. And it is, this thing is for over area, and this is for your height, that is Z0 to infinity. Now the same thing, if I consider just one column of the atmosphere with unit cross section, then it turns out to be this one only, that is 0 to infinity rho into CV into T D sigma for a column, for an atmospheric column, with unit cross section, and potential energy for the entire globe. This we got this expression, that is your rho density into acceleration due to gravity into height D sigma. Oh, sorry. In this case, then definitely this sigma will not be there. Instead of sigma, we will have the variable Z only. We will have the variable Z. Okay. For an atmospheric column with unit cross section. Similarly, here also, when I consider just an atmospheric column from Z is equal to 0, that is from mean sea level up to the top of the atmosphere, then it will turn out to be rho into G into Z. Again, for an atmospheric column with unit cross section. So now I can start with I. So I is equal to, we have seen this is equal to CV. I can take out because it is a constant 0 to infinity, and here it is rho into T dz. So what I am doing, I am just multiplying here R, that is specific heat for gas, and dividing. And again, if I use the equation of state, then this is equal to P. So therefore, I am having CV by R into 0 to infinity, E dz. Okay, E dz. So now this I can I can do little bit mathematical jugglery. I am doing that. This I can write like this, d of pz. So now for this integral, to set up the lower boundary and lower limit and upper limit of the integration, let us see at the What is our lower, where is our lower limit? Our lower limit is at mean sea level. At the mean sea level, z is equal to 0. Therefore, the value of the variable pz, here variable is this one, is equal to 0 at the lower limit. Now, where is the upper limit? At the where is the upper limit? At the upper limit is at the top of the atmosphere, and top of the atmosphere is defined, theoretically it is defined where the value of pressure is equal to 0. So therefore, at the top of the atmosphere, value of this variable, it will be equal to 0. That means that the upper limit will be also equal to 0. Fine. So, and this will be is equal to again z into dp, z into dp. So here again we have to fix up what is the upper limit, lower limit. So here variable is p, so therefore at the lower limit p is nothing but your PMSL, and at the top this will be is equal to 0. This will be is equal to 0. So therefore this will be is equal to CV by R, with a minus sign, PMSL up to 0, ZDP. Again, let me apply the hydrostatic stability. Hydrostatically stable means dP is equal to, this we know very well, this is equal to minus G into rho into dz. So therefore I can, if I apply here, then what you are getting, I will be is equal to CV by R, then it will be Z, sorry, minus sign is there, then Z, and dP is equal to minus G into rho into dz. So therefore what we are getting, minus minus plus CV by R, that is your, sorry, 0 to infinite. What will be the limit when P is equal to PMSL? That means we are at the bottom, Z is equal to 0, and when P is equal to 0, that is at the top of the atmosphere, Z is equal to very high, that is infinity. So here Z is equal to 0 to infinity, and G rho Z dz. Look at here, this is this integral, sorry, Z is equal to 0 to infinity, sorry, infinity. This integral is nothing but is equal to P. So you are getting this is equal to CV by R into P. So therefore ultimately what we are getting, we got I is equal to CV by R into P. And since CV by R, it is a constant, and we know that when two quantities are said to vary directly, now if one can be expressed as the product, as a scalar product, as constant product of other one. So here, since I is expressed as as P into something, therefore I can say I is proportional to P. So mathematically, though, very easily it can be explained. That is not a, and what we were discussing, and trying to understand it in an intuitive manner, because what happen, many times mathematical approach is not very much welcome. Many times, through my long experience, I have seen many times. So many times actually conceptual thing or intuitive method. So here actually that's why our approach was like this. So first, let me try to increase I, and let me lead to that, it is leading to that there is an increase in P. Then let me try to decrease in I, and then let me prove that it leads to decrease in P. This is number one. That means I implies P. I implies P. In logical, yeah, I implies P. And in the vice versa, now next stage, let me first try to increase P, and to show that this leads an increase in I, and in the same way decrease in P, which leads to decrease in I. So this again implies P implies I. P implies I. So and from these two, logically we can say that P is proportional to I, or I is proportional to P. So for that, what we have done, that how I will increase I. This is a air column. This is an air column which is extended from mean sea level up to top of the atmosphere. How to increase? For increasing I have to increase the temperature only. If I increase the temperature, then there will be expansion of any gas, and the gas will try to, that is air will try to move up, and when the air try to move up, then the height of the entire air's center of gravity, that will increase, and due to increase in this height, P will increase. In the same way, if I want to decrease I, next one, then I have to decrease the temperature of the air inside. That means I have to cool down the air. If I cool down the air will becomes heavier, and it will come down. As it comes down, then in that case, what will happen? The center of gravity of the air inside the column, it will come down, and as a result of which there will be decrease in Z, and then there will be decrease in P. So therefore any attempt to increase or decrease of I will lead to a similar increase and decrease in P. On the other hand, suppose you want to increase P. So suppose if you want to increase P, that means you have to set some upward motion. Now for setting of an upward motion will result in that convergence of air. And already we have seen from the internal energy equation that convergence leads to an increase in I. So therefore increase in P will result in increase in I. On the other hand, if I want to decrease P, so therefore there should be I need to set some sinking motion, and that sinking motion will lead to some outflow there, that is divergence. And we all know, we have already read, already seen that divergence results in cooling, that is decrease in I. Okay, so therefore again P implies I. So in this way, this thing, I hope now it is clear to all the students. So in both way we can establish that potential energy and internal energy, they are proportional to each other. And as I told you, that since they are proportional to each other, that means they only vary by a multiplying constant factor. Okay, they only vary. So due to that, a new quantity has been introduced. The name of the new quantity is total potential energy. Total potential energy, it is defined as is the sum of internal energy and potential energy. Internal energy and potential energy. So then in that case, it will be is equal to CV. You can write it, internal energy already you have written, CV by R into P, plus P is there. So therefore, ultimately it will become CV plus R by R, that is CP by CP by R, CP by R into P, CP by R into P. Or you can also express as, suppose if you put P is equal to R by CV, R by CV if you put, then you will get this will be is equal to CP divided by CV into I. CP by CV generally we denote it by gamma, so into gamma into I. So total potential energy can be expressed as gamma into I. So now let us consider, as we were discussing, that hydrostatically stable, statically stable and stably stratified. Stably stratified means that in the atmosphere, in entire atmosphere is thought of to be composed of different layers, one after layer, and heavier layers are below and lighter layer are above. Okay, so as a result of which we all know that if the heavier masses are settled down below and lighter mass above, so then in that case the center of gravity, center of mass, of this entire atmosphere column, which is hydrostatically stable and stably stratified, it will be at its lowest elevation. It will be at its lowest elevation. And another one reason for lowest elevation, because we have considered it is hydrostatically stable. That means there is no attempt of any vertical growth also. There is no attempt of any vertical growth. That means because in the upward direction, there is no net force at all. Hydrostatically stable means you are just nullifying the existence of any force in the vertical direction. Okay. So as a result of which, once the masses are kept like this, that heavier mass below, lighter mass above, due to which center of mass, center of gravity, naturally center of mass, we all know, this always lies towards the heavier mass only. So it will be at the heavier mass, that way at the below. So therefore, under this configuration of the atmosphere, center, that is height of CG above mean sea level, is least. I hope we all can appreciate it. It is least. If it is so, then in that case the value of P, it must be least. That means value of P in the reference configuration refers to the existence of two conditions, hydrostatically stable and stably stratified. So therefore, potential energy in a reference state is minimum. It is minimum. So since it is minimum, so then as I is proportional to P, so therefore internal energy in the reference state, that is also minimum. And therefore Therefore, total potential energy in the reference configuration, this is also minimum. But now question is whether all part of the atmosphere every time can it have a reference configuration? Answer is definitely answer should be no, because had it been there, then we would not have got any weather at all. If our atmosphere is always stably stratified and hydrostatically stable, then there will be no vertical development. And if there is no vertical development, so therefore there will be no cloud development, nothing will be there. So it is not so. Even though on average, if I take the average of the entire global atmospheric condition, then maybe approximately the configuration of the global atmosphere may be reference configuration. But if I consider a part of the atmosphere, for example, suppose Asian region, like the right now a South Asian region, if I take some part of the atmosphere, there actually actual configuration of the atmosphere, that is which we call generally observed configuration of the atmosphere, this may differ, rather it differs from the reference configuration. So that we express by saying that TPE observed configuration is not same as no, rather I should say observed configuration is not same as the reference configuration. Not same as the reference configuration. If it is so, then naturally total potential energy of the observed configuration must be different than total potential energy in the reference configuration. So if it is different, then either it will be greater than or it will be lesser than, but there is no chance of becoming lesser than this, because this is minimum. So therefore, these two statements lead us to conclude that total potential energy in the observed configuration is greater than the total potential energy in the reference configuration. Now, one thing I would like to tell you, when the atmospheric observed configuration differs from the reference configuration, then you remember reference configuration requires two conditions to be satisfied. One is hydrostatically stable, another one is stably stratified. Hydrostatically, more or less, it is hydrostatic stability condition is a very robust, very strong condition. More or less hydrostatically stable condition, more or less it remains over a larger area. But statically stable condition, it may differ. It may be different. Actually, when the atmosphere is stably stratified, that time the potential temperature lines are quasi-horizontal, more or less quasi-horizontal, actually quasi-horizontals. Potential temperature lines are quasi-horizontal lines. So I may say this is your theta naught. This may be theta naught plus delta theta. This may be your theta naught plus 2 delta theta, 2 delta theta. This may be theta naught plus 3 delta theta, etc., etc. It is different height. It is a different height. It may be at z is equal to z naught. It may be, it is quasi-horizontal. Okay. So as a result of which, if you consider any level, then at a given level, if you take two different points, at both the point, potential temperature are approximately same. That means no one is potentially warmer or colder than the other one. No one this is potentially colder or warmer than the other one. So therefore, there is therefore no question of setting up of any vertical circulation. But if the atmosphere differs from stable stratification condition, then potential temperature lines no longer oriented quasi-horizontally. Rather, they oriented quasi-vertically. Just like, it may be like this, theta naught. Okay, let me write, this is your theta naught plus 2 delta theta. Then this may be theta naught plus delta theta. Okay, and this may be theta naught. This may be theta naught plus 3 delta theta, etc., etc. So now, if I consider any horizon, any level, if I consider any level, I have taken any level, it is z is equal to something. Suppose z is equal to some zl like this. So at the same level, let me take 2 points. This is 1 point, this is 1 point. Now look at here, this point potential temperature will be theta naught plus delta theta by 2 like this. And this point, this will be theta naught plus 1.5 delta theta, almost. So therefore, what we find, this point is potentially warmer than this point at the same level. Due to that, what happened? A vertical circulation is set up. Vertical circulation is set up. It is in the vertical base. Vertical circulation is set up. Because actually somewhere I read that every system has a tendency to become stabilized. Every system. So now this system, they fail to become stabilized because of this orientation. They can be stable if these lines are turned down and these are turned up. Then only they will be again stretched horizontally. That means again they will come to the stability. But that requires some motion, no? That requires some motion. Now, this motion, execution and maintenance of this motion requires certain amount of kinetic energy. Where from that kinetic energy will be available? Yeah, this kinetic energy is available from the difference, from the excess of the total potential energy of the atmosphere and in the observed configuration above the total potential energy in the reference configuration. Reference configuration. This much energy, this much part of the total potential energy in the observed configuration is only available to convert into kinetic energy required to execute and maintain this vertical circulation. And this is known as available potential energy. And if that mathematical derivation of the available potential energy, it is little bit tricky, so I am not going into the detail of the mathematical derivation. Rather, I will concentrate on the final expression of the available potential energy. Okay, so final expression of the available potential energy, it looks like this. The available potential energy will be some constant values will be there. There will be some constant values which include your many things, which includes your that quantity kappa, that is R by Cp, then your gamma, then your pressure at 1000 HPa, that is surface pressure. So many things, constant values involving this, and one integration. This integration is from height 0 to height infinity, and the integrand looks like this: T prime squared double bar divided by 2 into P into sigma dz. It looks like this. P we can understand, it is the pressure only, and sigma is nothing but the static stability parameter. Sigma is nothing but the static stability parameter. Static stability parameter we may write in many ways. It may be like this actually, that your T by theta into del theta del P, like this, del theta del P. Okay, you may in many where you may find that sigma is equal to like this: G by T into your gamma D minus gamma, like this. Many expressions are there. Mainly it is a static stability parameter. Okay, static stability parameter. Its value may not be very high, but its sign is very, very important. Static stability parameter sign. If it is positive, that means if theta increases with height, in this case it is negative actually. Then that if it is positive, then it is a stable, and if it is negative, this is answer. Most important is this quantity, that is your T prime square over bar. This is nothing but the variance of temperature. Rather, I should say areal variance of the temperature. Areal variance of the temperature. Variance of temperature. So it's finding. I am just trying to explain how to find out. Let us consider any level. And at that level, suppose that at kth level, let us say kth level. Now at that level, at any arbitrary grid point, suppose temperature is equal to T I J K. This is the temperature at any grid point IG, horizontal grid point IG, at the vertical level K. So now there are many. Now what I do, first I take their average, areal average, J I N J. Let me take areal average first. Areal average of all T I J K. Areal average. So areal average. Now suppose this quantity, let me say that it is your some T bar at K, T bar at K level. Now I take their deviation Tijk minus T bar K. Take that and let me call it just T prime I J K. T prime I J K, and then I make it 10. What I do, I square all of them. And then what I do, I take its again areal average. That is 1 by Ni Nj. Areal average actually I can express in terms of integral also. Here for simplicity I have expressed in terms of just double summation Ijk prime square. If I do, so this will be nothing but your, you can understand, this will be nothing but your T prime square over what, isn't it? This will be the variance. But this variance, it will be the variance for the level K. Now, this variance, let me calculate for every level. At least for all the standard level, we can calculate. And at every level, I calculate this quantity and then divide it by 2p sigma. And then I add them. This will be grossly represent the available potential energy. One thing is very, very clear, that if there is no horizontal temperature gradient, because we can understand that T prime at any point, this is nothing but your del T del X into dx, or rather delta X I can say, plus del T del Y into delta Y. So therefore, if there is no horizontal temperature gradient, then both of them will be equal to 0. Then in that case, we can understand T prime will be equal to 0. So therefore, if there is no horizontal temperature gradient in any atmosphere, which we call barotropic atmosphere, for such atmosphere, this variance will be exactly equal to 0. So therefore, in a barotropic atmosphere, available potential energy is equal to 0. But in any case, in our real atmosphere, we do have horizontal temperature gradient. That means our real atmosphere is of course it is a baroclinic atmosphere. Now question is how much baroclinic it is. How much? For example, Ramchandra is an ideal sun in our history, and I am deviated from Ramchandra. That means I am not as good as Ramchandra. But how much bad I am? It can be measured by the difference between my character and the character of Lord Ramachandra. So here Ramachandra is nothing but your barotropic condition actually. So what happened? This deviation. So in a barotropic atmosphere, available potential energy will be equal to 0. And in a baroclinic atmosphere, available potential energy will be not equal to 0. So more the available potential energy, more the baroclinicity in the atmosphere. Okay, I hope I have been able to now. So therefore, one thing is very, very clear. This available potential energy is mainly due to horizontal temperature gradient. That is pakka. Now, not necessarily every time we may have the horizontal temperature gradient in both east-west direction and in the north-south direction equally. It may happen that in the east-west, generally, if you take the general picture actually, that over the globe, you may find that your east-west temperature gradient must be there, but as compared to east-west temperature gradient, north-south temperature gradient is much more. As a result of which, if we see the global isothermal pattern, we all may remember that global isothermal pattern are more or less parallel to the latitude circles. That means that horizontal temperature gradient in the atmosphere mainly is mainly in the north-south direction. When there is a north-south direction horizontal temperature gradient, suppose it is your north-south horizontal temperature gradient, if it is there, then this horizontal temperature gradient of course gives rise to certain type of available potential energy, and that available potential energy we call it zonal available potential energy. And as I discussed sometimes back during my baroclinic instability talk, that time we have seen that when there is some instability, when there is some eddies, then those eddy convert this north-south temperature gradient partly to east-west temperature gradient. East-west temperature. This horizontal temperature gradient, this horizontal temperature gradient gives rise to again some types of available potential energy, and this is known as eddy available potential energy. Eddy available potential energy. Actually, that from the available potential energy, there are many type of conversion is there. One is your that this available potential energy can be converted to eddy available potential energy, and this available potential energy can be converted to zonal kinetic energy also. Zonal kinetic energy also. And of course, eddy available potential energy, similarly, we are having eddy kinetic energy also. Eddy kinetic energy also. That means kinetic energy of the disturbance. And this is your kinetic energy of the mean flow. So many times we may find that eddy available potential energy is also converted to eddy kinetic energy. Look at here. In both the case, some type of available potential energy is getting converted to kinetic energy. This conversion is known as baroclinic energy conversion. And this conversion requires this mechanism. Suppose this is warm, this is your cold. Over the warm region, there should be rising motion. Over the cold region, there should be sinking motion, so that in the vertical, there one circulation is set up. This type of circulation we all know very well. We call it thermally direct circulation. So therefore, any types of available potential energy is converted to kinetic energy via some thermally direct circulation, TDC, thermally direct circulation. This is also known as divergent circulation. Of course, it is a divergent circulation. Of course, the because due to this rising motion, there will be some low pressure area. Due to that, there will be convergence, and hence it is then there will be some divergence. So it is a divergent circulation only. So we can say due to some divergent circulation, we call it divergent circulation. Similarly, here also it is due to some thermally direct circulation or direct that is your divergent circulation. it converted, divergence circulation. And of course, there can be conversion between these two also. These two also. So this completes my today's lecture, because I am supposed to talk only available potential energy. So I discuss all this thing about available potential energy. Thank you very much.
Thank you, sir.
Thank you very much.
So,
if
at
there is
present,
any questions,
yeah, just one they have asked is, could you suggest reference books for this?
yeah. Fundamentals of Atmospheric Energetics by Win Nelson.
Okay.
Fundamentals of Atmospheric Energetics by Win Nelson. WEINNEILSON. Win Nelson. Blue color book. Very nice book. And another one book is there. Ceaseless Wind by Dutton. Dutton. Ceaseless Wind by Dutton.
Maybe by the time we take our photos, there will be more questions. So I request everyone to switch on their cameras, please. Dr. Mohan, yeah. Tyagi sir, yeah. So Mrunal, will you take the picture? Okay. Thank you, Mrunal. There are still no questions in the Q&A box.
I tried to explain in a simple way also,
Yeah, yes, sir.
so that everyone can, and I tried to minimize use of typical, very critical mathematical thing actually.
There is one question. In the tropics, surface will be warmer at the... Oh, that is, I think, half. Sir, in the tropics, surface will be more warmer at the surface. But nothing else is being written. Surface
No, actually,
always.
I
Always.
understand that is always. No, actually, I think he has mistaken one. This temperature gradient is not upper level and lower level. It is north, south or east, west. It is north, south or east, west. It is not above and below. Huh?
Yeah, I think Josan has got the answer.
Many times, actually, what happened that the people who are staying in a what is called coastal station, enjoying sea bridge, land bridge. So that is weakening of the sea bridge, land bridge can be attributed to the increased or decreased baroclinicity at the local level, which can be measured by monitoring day to day this available potential energy. And this is very simple thing, not necessarily entire portion I have to do. Suppose if I am staying at, say, East Coast, so covering East Coast, I can have a square. Over this square, on a routine matter, as a routine thing, actually every day we make compute that quantity that which I have shown, that is t prime over what, t prime square over what, this one itself, its integral, different level. So not simply we can calculate this t prime square over what for some standard isobaric level. But one thing we have to confirm, those standard isobaric level data should be every day available. Nowadays, gridded data is available there. You calculate and you make it a table. And I am 100% sure whenever you find some significant difference in the strength of the sea bridge, you can attribute it to this thing. 100% sure. And I think many graduate students can be given this project work also. This project work, it is a very simple calculation. Nowadays, data free is available freely, and it does not require a very hi-fi computing also. Nothing is there. It is possible.
Thank you, sir. Maybe we can also suggest giving this type of things to our MSc MTech students. So if there are no more questions,
Okay, thank you.
sir, I'll request now Mrunal to please moderate the vote of thanks.
Thank you, ma'am. I will just share my screen. On behalf of organizing committee, I would like to express our heartfelt gratitude to each and everyone for your contribution to this 21st lecture of the weekly online series on atmospheric dynamics and its application to climate science. Firstly and foremost, I extend my sincere thanks to Dr. Mandira Shrestha ma'am, Joint Secretary of SAMA Nepal, uh, for her welcome address and for sharing a brief overview of this lecture series. My deepest appreciation goes to our speaker of a day, Dr. Somenath Dutta sir, for delivering very informative lecture on available potential energy using a digital whiteboard, creating an interactive classroom-like session for all attendees. I would also like to thank Dr. Rohini Bhavar for moderating today's session and for Dr. Divya Prakash for managing the Q&A session. Special thanks to all the panelists and EC member for their guidance and constant support for every minute details. I also extend my thanks to all the participants and attendees who joined us across the globe. Last but not the least, heartfelt thanks goes to team member of Savitribai Phule Pune University for their dedication and behind the scenes efforts in successfully organizing this session. Thank you, ma'am. Thank you, everyone.
Thank you, Mrunal. So today's lecture is over. Very few lectures are remaining, so I request all the participants to please attend all the lectures. And in August, we will have the exams also. Sir, they are requesting if some notes can be given from your side.
Yes. I will give. Today night I will give. I
Okay,
forgot.
so that I can share then on
I
Monday.
forgot.
Okay.
I should have given.
Right, I would like to say additional gratitude to Dr. Somenath Datta because
Sad.